Alright, so related rates. The key to these problems is to be very neat in your work. Take the time to write out what you know and what we're trying to find. Like that very last homework question, when anybody asked me about it, I said, okay, let's start making a list. You know, P is this, P prime is this, V is this, and we made a list of all of our variables. That's what we have to do in order to be successful in these problems. So, what a related rate is a problem where you have multiple quantities that are changing throughout time. So I have the definition on here. It involves two or more quantities that vary with time. So I may have an equation that has an x and a y and a z. And I'm going to do the derivative of everything with respect to time. I want to look at over time. How are x, y, and z changing? If we're talking about like if I were filling a pool with water, I could look at how the volume of that changed over time, how the height of the pool changed over time. So I can look at how all these things are changing as time goes on. Our strategies, if possible, we might need to draw a picture. So if that helps, we will do so. We are going to write down all the values that we have. When I am grading tests and quizzes, I am going to give you points for saying what everything is and correctly identifying that. Then we are going to have to write some type of equation. A lot of times that will be kind of based on our picture. If I'm filling a pool, if it's a rectangular prism, if it's a box, then I'm talking about volume equals length times width times height. If it's a round pool, then I need the volume of a cylinder. So we have to look at our picture to know what kind of equation we need. Then we'll do our derivative and plug in all of our values. You cannot plug in the values before the derivative. Why? If I plug in my value, then it's a constant. What's the derivative of a constant? 0. The only things you can plug in are things that never change. So if I were talking about my pool, if it's just a round rectangular, cylinder, then the radius of that would never change, right? But if I were talking about like filling a funnel or something, the radius is changing as you move up the funnel, so I couldn't plug in my radius until after the derivative. So the only things you can put in are constants, the things that aren't changing. Alright, so here is our first example. I recommend reading through these first, and then we're going to kind of go back and pick out the information. So air is being pumped into a spherical balloon so that the volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so let's go back and identify any values given to us. Okay, so I've got a few things here. Volume, so let's just make it easy. If I'm talking about volume, that's a V, right? The volume increases at a rate. Anytime I'm talking about a rate, what is that? A derivative. So it's like the derivative of volume. You could call this V prime, but I'm going to label it slightly different. I'm going to call it dV dt. Okay, it's just another notation for derivative, but I really like using that in these related rates problems because your units kind of tell you how to label things. Cubic centimeters, that's talking about volume. Seconds is talking about time. So dV dt, volume over time. It's increasing, so it's a positive. If it were decreasing, it would be a negative. Okay, I want how fast the radius is increasing. So I want to find something about the radius. I want to know how it's changing. So what would that be? Am I just looking for r? No, what am I looking for? The derivative of r. I'm going to call that dr dt. That's the thing I'm trying to find. When the diameter is 50. Okay, I've talked about volume and radius here. I probably don't want to introduce another variable. I don't necessarily want to use diameter, but what can I get from the diameter? The radius. If the diameter is 50, what's my radius? 25. Okay. So I'm talking about a sphere. Does anybody remember the volume of a sphere? 4/3 pi r cubed. Again, we're getting into these. I will give you anything, like on a test or quiz, I would give you this one. You know, things I would expect you to know would be like area of a circle, area of a triangle, rectangle, those. Volume of a rectangular prism, you know, volume of a box, length times width times height, you should know that. But anything too much different from that, I'm probably just going to give you the formula. Okay, so we have everything. We could draw ourselves a picture of a balloon, but I don't think it's really going to help us on this problem. After we have our equation, what do I need to do? Derivative. Now, we are doing all of these in terms of time. So the only variable that would turn into a 1 when I did the derivative would be t. Everything else, remember that implicit differentiation we were doing before break, every time we did the derivative of a y, we had to put a dy dx with it. We're going to use implicit differentiation. We want the derivative with respect to time, so the derivative of v is dv dt equals 4/3 pi, that's just a coefficient. So all you have to do is bring down your cube. So 4/3 times 3, you get 4 pi r squared. But what do I have to put with my r? dr dt. Remember, everything except the t gets this. Any other variable other than a t would be something dt. That's our derivative, so now we plug in our information. dv dt is 100 equals 4 pi, my r was 25, squared dr dt. Okay, so we work this out. 25 squared times 4. So we would get think you guys are checking my math, right? 25 squared is 625 times 4. What do I need to get dr dt by itself? Divide the 2500 pi. So my dr dt equals 1 over 25 pi. I do want units on all of these. But the nice thing is when we use these labels, the units are kind of come easy. Because the top was r. What would be the units of a radius? Centimeters per. T was time. What were the units in time on this one? Second. So it's centimeters per second. What questions do you have for me on that labels are important. If you label things, it is much, much easier. I tried to put a blank slide after each of these if you guys need extra space, I think. Okay. Let's look at this one. Suppose that x of t and y of t are the x and y coordinates at time t of a point moving around the circle x squared plus y squared equals 25. Differentiate with respect to t. So this one I kind of gave you the equation already. There's no trying to write the equation. I gave it to you. I'm asking you to do the derivative with respect to t. So that means when I do the derivative, if I have a t, its derivative would be 1, but anything else gets a d something dt with it. So the derivative of x squared would be 2x plus derivative of y squared derivative of 25. 0, it's a constant. Okay, that's all the first thing asked for. Second question. Now I'm giving you some values. X is 3, y is 4, dx dt is 12. Find dy dt. So we're just going to plug them in. So we had 2x, so this was our equation. So my x is 3, dx dt is 12, 2, y is 4, I do not know dy dt. Did I give you information to find or about units on this? No. I just want to show you something here. So this originally was a circle with a radius of 5. Okay, we are at the point on the circle when our x was 3 and our y is 4. So we are right here on this circle. Dx dt was a positive 12. That meant my x was increasing. So which way am I moving on this circle? My x is going up, I'd have to be going this way for my x's to get larger. And so does it make sense then that my y dy dt is negative? As my x's are increasing, my y's are falling here. Likewise, if my x had been a negative, you'd be traveling this way, so dy dt would have been a positive. Okay, so this dx dt, dy dt tells you how those variables are changing. Any questions there? I want you guys to take a second. This one's a little more challenging. I want you to take a second and read it and see if you can draw a picture that kind of represents what's going on. Okay, if you're not exactly sure, that's okay. Let's see how we do that. A rocket that is launched vertically. So this is where we launch from. This is my launch site. If it's launched vertically, that means it's going straight up. There's our rocket going up. Is tracked by a radar station located on the ground 3 miles from the launch site. So if it's on the ground, that would be horizontal for my launch site. 3 miles away. So here's my radar station. What is the vertical speed of the rocket at the instant that its distance from the radar station is 5 miles and this distance is increasing at a rate of 5,000 miles per hour? So we have a triangle here. I want to be careful. In my picture, I want to use variables to label anything that's changing. And anything that's a constant, I can label as a number. Okay? This height of the rocket, is it changing or is it constant? Changing, because the rocket keeps going up. So let's call that something. What do you want to call it? X. Okay. The distance between the launch site and the radar station, is that constant or changing? Constant. How far apart are those? The distance between the radar station and the rocket, constant or changing? Changing. As the rocket goes up, that's going to change. So let's call that a y. Okay. Now let's go back to the problem. We've used the 3. What's the vertical speed of the rocket? So speed is talking about the derivative. The vertical speed, so I'm talking about this x side, so what would I label that? That's the thing I'm trying to find. What's the vertical speed, so I do not know. At the instant that its distance from the radar station is 5. What variable represents the distance from the radar station? Y. So at the instant when my y is 5. And this distance is increasing. So what variable would I use for that? dy dt. How is the y is changing at a rate of 5,000 miles per hour. So dy dt is 5,000. Is everybody with me here? So we have to write some kind of equation. Looking at my picture, I have a triangle. What kind of equation could I use? Pythagorean theorem. You know, things with triangles, I could do like area of a triangle, but do my variables ever make a mention of an area here? No. So I don't want to introduce new variables into this. I only want to use the things I already have, the x, the y, and the 3. So this would be a right triangle because it went straight up from the ground. So we could do Pythagorean theorem. A squared plus b squared equals c squared. So x squared plus 3 squared equals y squared. Or you could say x squared plus 9 equals y squared. What do we need to do from here then? Derivative. Derivative of x squared would be? Derivative of 9? 0 equals derivative of y squared. Okay. Now here, if we plug in, I don't know x, I don't know my dx dt, I gave you the y, and I gave you the dy dt. I can't solve for both x and dx dt at the same time. What am I going to do? I'm talking about the particular instant in time when this side is 5, this side is 3. Can you find what x has to be at that instant? Yes. So if we needed to find the x that went along with this, we could do x squared plus 3 squared equals 5 squared. So x squared equals 16. When you do the square root, you would do plus and minus, but would x be positive or negative here? Positive because it's going up. So the x at this particular instant is a 4. So even though I didn't give it to you, you had everything you needed to solve for it. Get 6250. Units. Dx dt. X was the height. What were we measuring our heights in? Miles. Per, t was time. What was I measuring time in? So my x is going up at a rate of 6,250 miles per hour. Is that one all right? I think I'll do one more problem and then we'll stop for today. Take a second and read it and see if you can draw the picture. A ladder resting against a vertical wall. So it looks like this. Where does the ladder go? Okay, it's the hypotenuse here. So does the length of my ladder change? No, so we can go ahead and label it. It's 10. Alright, so what's happening is this ladder is sliding. So as it slides, the top is going to go down and the bottom is going to go out. So do these sides, are they constant? No, so they need variables. Let's just call them x and y. Doesn't matter which is which, however you prefer, so I'm just going to say x and y. If you did them backwards, that's fine. Okay, so now the bottom of the ladder. So if I have the bottom here labeled as x, if I'm talking about how fast it slides away, that would be derivative of x, dx dt, slides away at a rate of 1. How fast is the top of the ladder sliding down? So that would be, would we expect a positive or a negative here? Negative, because it's going down. Okay. When the bottom of the ladder is 6 feet from the wall, so we're looking at the instant when my x is 6. Okay, we're going to have to find our y eventually, aren't we, just like the last one? So how would I find y for that particular instant? Pythagorean theorem. So it would be 6 squared plus y squared equals 10 squared. So y squared equals 64. Is my y positive or negative? Positive. It's just the height. So at that particular instant, my y will be an 8. So again, our formula is the Pythagorean theorem. X squared plus y squared equals 10 squared. Or you could just write that as 100. We do our derivative. Derivative of x squared would be 2x dx dt. Derivative of y squared is 2y dy dt. And what is the derivative of 100? 0. plug in. X is 6, dx dt is 1, y is 8. We do not have dy dt. So 16, y dt is negative 12. If you divide by 16, get a negative 3/4, which we predicted it would be negative. Units. Y was the height that was measured in feet. Per t was time, that was in seconds. So it's going down at a rate of negative 3/4 foot per second. How are we doing with this stuff so far? The assignment, you're ready to try just a few problems. So the day 1, 2, 4, and 5.